How's it going, ladies and gentlemen? Mr. Donnie here with some 13.1 and 2 problems talking about solutions. All right, quick one here, only 4 questions. The dissolution of water in octane is prevented by blank. All right, well, dissolving is pretty much, interaction between the solvent and the solute. So if we have this octane, which is a really non-polar molecule, and we have water, which is polar and it has hydrogen bonding, they're not really going to mix. Water's not going to dissolve into that because let's say we got the nonpolar molecules and then we got H2O mixing around with them. Well, there's not really going to be any interactions between the water molecules and the octane, but there is going to be really strong interactions between water molecules and other water molecules because of that hydrogen bonding. So the water is going to want to hang out with other water, and it's going to not really mix with the octane at all because of the hydrogen bond interactions between the water molecules. So choice B. All right, let's see. Lambda dispersion forces between octane molecules. Yeah, there will be dispersion forces between octane molecules, but that's not really going to be why the water doesn't dissolve. Right, that's not so much. Dipole-dipole attraction, non-existent because it's not polar. Ion dipole, there's no ions. Repulsion between like charged water and octane molecules, not quite. All right. 2. The phrase like dissolves like refers to the fact that it's B. Polar solvents dissolve polar solutes and nonpolar solvents dissolve nonpolar solutes. That's, this is why oil and water don't mix, right? Plus no H2O, right? Because water is polar and oil is nonpolar. So that's why they don't mix. That's why they don't mix with each other. If you were to ask, well, why does the water rise to the top? Well, then that would be density, right? It would be less dense, which is why it's on top and water is on bottom, but that is not why they don't mix. They don't mix because oil is nonpolar and water is polar. 3, the formation of solutions where the process is endothermic can be spontaneous, provided that. So remember, endothermic, that is not favored. Not favored. So reactions, in order to be spontaneous, generally have to well, what's favored? Let's start there. What's favored by nature? We like exothermic reactions and increasing randomness or entropy. A reaction that is both will always be spontaneous. A reaction where it's one or the other will sometimes be spontaneous, and reactions where neither of them are spontaneous will never be a reaction where neither are favored will never be spontaneous. So if we have something that's endothermic that's not favored, well, then that entropy better be favored. It better increase the disorder. It better become more random. So which one is that? C. 4, last one, a saturated solution is blank. It's a definition question, all right? It's C. All right, there's a couple of good wrong answers on there, right? Saturated solution, if you didn't read A closely, it says contains as much solvent as it can hold. That's the wrong word. If it said solute, then you'd be, you'll all right, cool, that could be the answer, but it says solvent. So solvent's the thing that does the dissolving. Solute is the thing that gets dissolved. Contains no double bonds. That's got nothing to do with saturated solutions. Will rapidly precipitate if a seed crystal is added. That's describing a supersaturated solution. All right, and cannot be attained. That's a lie. All right, so saturated solution. You can picture this. You ever make Yoo-hoo? And Nesquik, and if some of it becomes more dissolved, then some of it precipitates out and goes back down. So this is a saturated solution. Whenever you have a solute chilling at the bottom, you know you have a saturated solution because, well, what what is that stuff doing down there? Well, there's already so much in the solution that it can't dissolve anymore. And that's the definition of saturated. All right, well, that was quick and painless. See you in class.